Good day. I hope you are keeping well. Today I'm going to discuss Worksheet 5. And here are the first question in Worksheet 5. We have a function of two variables and we have two jobs. The first job is to show f is differentiable at the point 4, 2. And then after doing that, we have to find the equation of the tangent plane at the point 4, 2. Now, we can use a long way to show f is differentiable at the point 4, 2, or we can use theorem 67. And like a table, Theorem 67 has four parts. So I'm going to use theorem 67. I'm going to solve by saying, okay, let D be the entire plane and this is open. And now for the first part, I can say that f partial x exists on D. In effect, you can actually work out that f partial x that's equal to 2x minus y. The second part is f partial y exists on D. And we actually have a formula, f partial y, that is equal to minus y plus 2y. And then also, f partial x is continuous at the point 4, 2, because f partial x is a polynomial. We know polynomials are continuous everywhere. And then f partial y is continuous at point 4, 2. Again, it's a polynomial, so it's continuous everywhere. So, by theorem 67 in the textbook, we know f is differentiable at the point 4, 2. All right. Now that we know that f is differentiable at the point 4, 2, we can find the equation of the tangent plane. And as we saw in the textbook, there's a neat little formula for the equation of the tangent plane. So the formula is z is equal to f at the point plus f partial x at the point times x minus 4 plus f partial y at the point times y minus 2. And I'm going to leave it to you to verify that you agree with my calculation. I get that the equation of the tangent plane is z is equal to da, 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 sorry about that. It's 12 plus 6 times x minus 4. Alrighty, let's move on to B. Now B is asking for all points on the surface where at that point, if we draw a tangent plane, it's perpendicular to another plane. So we are dealing with two planes in this question. So we know that two planes are perpendicular if and only if the dot product of the norms is 0. So we need the normals of each plane. So normal of tangent plane is, let's call it N1, that is minus f partial x at the point minus f partial y at the point, comma 1, which works out to be y minus 2x, x minus 2y, comma 1. Now the normal of the plane x plus 2y plus 3z equal to 4 is, let's call it N2. It's a coefficient of x, it's a coefficient of y, and it's a coefficient of z. All right? Now, planes are perpendicular if and only if the dot product of the norms is 0. And so that means that y minus 2x, x minus 2y, comma 1, that's one vector dotted with other vector 1, 2, 3 equals to 0. Now, if you do this calculation, I'm going to leave it up for you to verify. That happens when y is equal to 1. Now, what does this mean? Well, this means that we want all of the points on the surface where the y value is equal to 1. Now, we can say the points are, and it's on the surface, so the set of points where this value can be anything, let's call it p, second value is 1, and the last value would be ft1, where p is a real number. So this creates all of the points on the surface. We can actually write this in a nicer way. We can say the x value is t, the y value is 1, and the z value works out to t squared minus t plus 1, where t is a real number. So you see in this case, there are infinitely many points on the surface with this property. All right, and this is now question 1. Now let's move on to question 2. Question 2 is the following question. Again, we have a function of two variables. If partial x is always a, if partial y is always b. And the question asks, part A, why is the domain of f r squared? Well, quickly, remember that the domain of f partial x is all of the 2D vectors such that f partial x at that point exists. So bearing that in mind, it is quite clear that the domain of f partial x should be a subset of the domain of f. And we know because this is a function of two variables, this must be a subset of r squared. Likewise, we are told that the domain of f partial x that's equal to r squared. So this gives that the domain of f is the entire plane, which is what you are asked to prove in this question. Now, moving on to B, it's a little more tricky because we got to use the mean value theorem for a function of two variables. And with this given information, we got to prove that if all of this is true, that f is actually a plane. Now, where to start? Well, let's start with an object point A, B, B. Now, let's start to do the following. If you look at this theorem provided here, we have way too many variables. So we've got to be a bit smarter. So let's do the following. Let AB be the origin. So immediately we have far fewer variables. And let HK be a 2D vector, which is not the origin. Right. So if we apply this theorem, we get that f of h minus f of naught naught is equal to h f partial x at the point theta h comma k plus k f partial y naught theta k times k. Now we're in a happy position because we know that f partial x exists everywhere, that's equal to a. We know that f partial y exists everywhere, and that's equal to b. So remember that if the theta h and theta k for some values between 0 and 1. By theorem, let's have a quick peek. That is theorem 65. We end up getting this. So we end up getting this equation. And now we can be smart. We can say the following. Let h be x, let k y, b, and let f naught naught equal to c. So we obtain following equation. Do this, we get that fxy minus c equal to hx plus ky. And if fxy is equal to z, we get z is equal to hx plus ky plus c, which is an equation of a plane. And isn't this what we are after? All right. Remember, this is true for any x and y. And so, using the special case of the mean value theorem for a function of two variables, we obtain that indeed, if all of those conditions are true, we do end up with a plane. All right. Remember, you can pause, rewind, go forward, and re-listen to these explanations. All right, now for the very last question is the following. Again, we have a function of two variables, the square root of the absolute value of x times y. Now, first up is to show that the directional derivatives exist if and only if u1 times u2 is equal to naught. So this is an if and only if. So we've got to be very careful how we approach this. All right. Now, if the directional derivative exists, then the limit as h goes to naught of f of naught plus hu1 naught plus hu2 minus f of naught naught over h exists. And this gives us the following, that the limit h goes to naught of the square root of absolute value of hu1 times the absolute value of hu2 all over h this. And if we simplify this, we get up the limit as h goes to naught of the square root of the absolute value of h squared over. So we multiply the x value and the y value, and we end up getting this times. So be very careful here. We have absolute values, so this exists, and so this gives us a h times naught of the absolute value of h over h, the square root of the absolute value u1, u2 exists. All right, now if u1 times u2 is equal to naught, then we get that the limit h going to naught of the absolute value of h for h times naught, which is naught, which exists. Thus, the directional derivative of f at the point naught naught in the direction of u exists. However, if you look at the limit h going to naught plus of the absolute value of h for h, that is equal to the limit h going to naught plus h of h equal to 1, and the limit h going to naught minus absolute value of h over h is equal to the limit h is equal to naught minus h over h that's equal to minus 1. So thus, the limit h going to naught of the absolute value of h over h do not exist. And this is very important because if u1 times u2 is non-zero, then from above, the limit as h going to naught of the absolute value of h over h times the square root of u1 times u2 do not exist. This means, this is very important, that the directional derivative of f at the naught naught in the direction of u do not exist. Together, this shows that the directional derivative of f when 0 exists if and only if u1 times u2 is equal to 0. Very important. We show that if u1 times u2 is 0, then the directional derivative exists. But if u1 times u2 is non-zero, then the directional derivative do not exist. So be very careful in answering this question, that you treat both cases when the product is 0 and when the product is non-zero. All right. Now for the last few questions is very easy, because the question asks, is f differentiable at the origin? So yes, two of the directional derivatives exist, but we can immediately say no, since some directional derivatives do not exist, by theorem 21, we can say if has no tangent plane at the point 0, 0. Alrighty, and now for the very last question. The question um, is does f have a tangent plane at the origin? Again, make sure you know the definitions and the concepts quite well. And immediately we can say no, since f is not differentiable at origin. All right. I hope this session was useful. Have a lovely day, and please listen to this video again. Cheers from me, Dr. Wiggins.